Now next is Boger correction. In Boger correction, right, in the previous correction what we did, the elevation difference, station number 1 was here, station number 2 was here, right, which means this is the ground surface. What we did, we assumed that only air was present, and then since the value which we have measured would have been less here, we plus some correction we made and brought it to this level. But in this way, we assumed only the presence of air here, but in fact what was there? There was some additional mass of earth present here, which was ignored in the previous correction. That is also accounted in Boger correction. Boger correction accounts for the effect of rock mass, right, by calculating what is the additional gravitational pull exerted by this slab of rock, right. So, you recollect in the previous, this was station number 1, this is station number 2, station number 1 value 1 is here, station number 2 is here. In station number 2 there is some additional rock mass which also we consider. How we can consider this? By knowing the elevation difference as well as the density, right. That is, the elevation difference is h and the mean density of rock is rho, right. When you have these two, then we can carry out the Boger correction. So, now what do we say, or what do we understand? Though station number 2 is away from the center of the earth, station number 2 is expected to have higher acceleration due to gravity, because station number 2 has additional mass of this much of thickness, right. This is accounted for in Boger correction. How we do the Boger correction? So, Boger correction is done as per this relationship, where 2 pi multiplied by gravitational constant multiplied by the density multiplied by the thickness. G is the gravitational constant, right. Suppose if you assume, right, Boger correction is approximately 0.4192 rho h in gravity units, right. If you assume the height in meters, if you assume the height in feet, the gravity correction will be 0.01277 rho h. Okay. This will be the gravity correction for Boger, right, as per this was suggested by Bohr. So, Bohr correction accounts for the impact of additional slab of rock, right. So, on land Boger correction is, right, is in mg per meter cube and h is in meters, whereas in sea h is the depth of water, right. So, in land, if you see station at higher elevation, gravity value will be higher due to additional mass of, I will draw, this is the ground surface. Let us assume as ground surface, this is station 1, station 2. Station 2 has got additional mass of material. So, acceleration due to gravity will be high due to the additional mass of slab compared to 1. So, the value which we have obtained here has to be subtracted. We have to give minus, right, minus value, right. If the station is lower, right, let us say this is station number 3, because it does not had any mass compared to station 1, we have to assume some additional mass here. So, the value have to be added here it has to be subtracted. with reference to this is our reference station or base station, right. So, this is how we carry out the correction. So, if you see kind of in the first case in free air we are subtracting, here we are adding. So, combinedly we carry out a correction which is known as free air and Boger are added together and it is known as elevation correction, right. One will be minus, another one will be plus, both will be combined, that becomes elevation correction. Is it clear? So, this is, we have seen what? First we have seen latitude correction, number 2 we had seen free air correction, here in this slide we have seen Boger correction, right. Next is terrain correction. This is very interesting, right. Actually, the topography around our measurement station also play a role on the value which we have obtained, right. Generally, what we have done in the previous case, in Boger correction, we have just assumed a subdued topography, right. That means we have not literally taken into account of the actual topographic variation around our station, right. Actually, we need to do some additional terrain correction, right, to overcome the effects of mountains and valleys adjacent to our gravity station, right. So, in fact, the mountains and valleys and up to 22 kilometers from our gravity station will have a impact on the measured value, right. That means we have deployed the gravimeter, let us say at station, at a particular station, adjacent to that, not adjacent, at 20 kilometers from that gravity station there is a hill. There will be an impact of that hill on the gravity reading which we are going to take. That means mass in our gravimeter is going to be attracted by the hill which is at 20 kilometers, which has to be also corrected for. That is what is known as terrain correction. So, generally it is assumed beyond 22 kilometers, the effect of topographic variation is assumed to be negligible. So, we need to consider the topographic effects around our gravity stations up to a radius of 22 kilometers. So, we can understand about the terrain correction much better from these diagrams, right. Imagine if a station is next to a mountain. So, this is our station. This is our gravity station. We have deployed our, this is our gravimeter. The mass in the gravimeter, right, that is the small m. The mass in gravimeter is also attracted by the mass of the mountain, because this is the adjacent mountain. This adjacent mountain attracts the mass, okay. So, there is an upward force on the mass in the gravimeter. What it does? It will eventually reduce the reading which we are measuring, because in the, suppose if there is no mountain here, if there is no mountain right here, the gravity value is little bit higher. Because of the mountain here, gravity value is little bit reduced. Why? Because the mountain also attracts the mass in the, this is the resultant direction, okay. This is the gravitational pull, right. The mountain also attracts. This is the resulting force which we are measuring. So, what will happen if the gravity station is adjacent to a valley? Now, imagine this is our gravity station. Adjacent to that there is a valley. This is a valley. Previously, we had a mountain. So, now we have a valley, right. So, in a valley, what happens? This mass is attracted by the Earth's gravity. But what had happened here is, adjacent to our gravity station, there is no material present, only air is present. Why? Because it is a valley. Due to this reason, this gravimeter is measuring slightly reduced gravity value because the mass is absent here. There is no mass here. So, that is, there is an absence of downward force on the gravimeter as we had assumed in Boger correction. In Boger correction, we assumed a presence of a thick slab, but the slab is missing here. The gravity value which we are measuring here is slightly lesser. So, what we need to do? We need to correct for these effects. So, in fact, in terrain correction is always positive, regardless of whether you have a mountain or valley. Let us see, here is a mountain. In the first case, there is a mountain. This is our gravity station. The mountain is attracting the mass, due to which the value we have measured is less. So, we need to add for correction. Here, what had happened? In the second case, adjacent to our gravity station, there is a valley. Because of the presence of valley, the gravity value which we have measured is little less because there was deficiency in the mass. So, here too the correction is positive. In both the cases, that in terrain correction, the correction is always positive whether the station is adjacent to a valley or a mountain. Is it clear? So, these are all the corrections that we need to be applied for the gravity data. To understand terrain correction much better, we can have a look at this diagram, right. So, this is the actual steady site. Now, imagine a gravity station is at a elevation high h. This is going to be our station number 1. It is above the reference plane. How much above? By high difference of h. Now, what we are doing is, in this correction, right, while doing Boger correction, what we have done is, we assumed only this height. Let us assume h is equal to 10 meters. What we have done in Boger correction, we assumed the presence of a infinite slab. Actually, we have to account for the presence of this mountain, right. See, the region A is considered in Boger correction. Actually, A is not there, isn't it? Similarly, if you take B, this region B has to be accounted for, which is present but which was ignored in Boger correction. Hence, Boger correction has over-corrected these regions. Region B consists of rock, right, that exerts upward force leading to reduction in the gravity value, isn't it? So, this thing we are getting rid of these issues by carrying out terrain correction. So, in terrain correction, we carry out a correction to eliminate the effect of B as well as region A. So, this is what is known as terrain correction. So, in terrain correction accounts for the error caused by region A as well as B. Is that clear? Because previously in Boger correction, though the surface was like this, our gravity station happened to be here. So, we assumed a infinite slab. We eliminated, we forgot this, and also we added this which is not there, that is region A. We are overcoming these issues by carrying out terrain correction, right. We have accounted for both A and, right. So, we have seen, first we had a look into latitude correction, then we had seen free air correction, Boger correction, lastly terrain correction. Then what next? how we can carry out the terrain correction. Terrain correction is carried out usually using what is known as a Hammer chart. Hammer chart is nothing but a template in the form of a circle. The diameter of the circle is 22 kilometers. Right, this is the zoomed version of this inner part. What does this circle has? This circle has got several sectors, several regions. Terrain correction is made by assuming what is the average elevation of this region compared to the center. Let us say elevation at the center is 20 meter MSL. Here this region is 23 meters. This region is 21 meters. Here 20 meters. 20 meter means it is same. So, no impact of this part. This part is minus 10 meters. This is how we determine the average of each sectors, and we also need to know the approximate average density of the rocks beneath that by taking into account of the density and the elevation difference from our station which is at the center to these sectors, we arrive at the elevation correction. Though it appears to be complex, it can be done very easily because we can carry out the correction using the digital elevation model which we have for the entire world using some simple software. So, we determine the mean height difference from the digital elevation model, and the total correction is made by contributions from individual sectors, individual sub-regions of this Hammer chart. Right? What is the effect of each region or compartment on the reading which we have taken at the center is determined. This can be done very easily nowadays using some simple tools, taking the help of some computer programs. Right? Our station is here. The computer program will make use of the digital elevation model which we had obtained for the site and automatically calculate and we need what else we need to give? We should also give the density. So, after giving the density of each sector, it will carry out the total correction that need to be given for the data we have obtained at the center. Right. So, we have seen, first we had seen latitude correction, then we had seen free air correction, Boger correction, terrain correction. Right. Then the next, I did not tell you at the beginning, this is what is known as tidal correction. Right. The earth, solid part of the earth also responds to the pull by the other planets, just like oceans. In oceans, we have tides. Why do we have tides? Because of the interplanetary pulls, attraction, right? Water is attracted by the other planets, which we could visually see, but the similar response of the surface of the earth we are unable to see because it is very, very small. What we see on the ocean, same tidal effects are also happening on the land part, but the impact is so less we are unable to see, however, which also need to be accounted for in gravity survey. That correction is known as tidal correction. Right? They also affect the gravity reading which we have made. Right? Since the earth is solid, right, very rigid, the rise and fall of the surface is very, very minute. Very minute rise and fall. So, gravimeters are very sensitive. They are able to pick up these variations. Right? That means they are able to pick up the tidal effects on the solid part of the earth. We have to correct for that. Usually, changes due to the tidal effects, that is due to the locations of sun and moon, will be about 0.3 to 0.3 milligauss, which is reasonably of higher order of value, because what we are trying to achieve, we want to understand what is the gravity variation due to the change in the gravity of the change in the density of the rocks present below the surface. That is what we are looking for. So, in order to look for that, we have to eliminate the effect of these tidal variations, right. So, this is carried out by understanding what is the drift of the equipment. That means, what do we mean by drift? How the equipment performs at different times. We had already seen drift. Do you recollect? We had already seen what is the drift in the equipment. What we had seen by drift? With respect to time, how the G values were varied at different times. We had seen previously. When you collect the drift information, this also accounts for tidal variation, right. How we are going to see here, right. So, here, right, we see an image, right, published in this book, right, where you can see the value which we have measured at the surface of the earth. That means, imagine we are at one site number or station number 1. At station number 1, we are repeatedly collecting information, right, from 6 a.m. to 6 p.m. Maybe we visit the site at 6 p.m., then maybe at every 6:30, 6:45, 7:15. Like that. So, we are collecting information at different times. Now, this is the value we have got. This curve is known as drift curve. Why there is a variation in the value of the G we are measuring, right. So, here we are showing you the relative gravity value. Relative gravity value varied from one time to the another time, because for change with respect to change in time, the gravity value varies due to the changes in the location of sun and moon, and also due to the problem within our instrument. Though the gravimeters are manufactured taking care of so many issues, I had also mentioned gravimeters are also temperature controlled. The temperature within the gravimeter can be maintained much above the expected atmospheric temperature during our period of survey. In spite of all this care, the equipment can show some minor variation in the values when you repeat the measurements at different times. For this purpose only, I told you previously, if this is our steady site, right, these are all our gravity station, we select one site preferably at the center as base station, right. We commence our survey in the morning at 6 a.m. We start measuring here, then after some time you go back to base station, then come back, do some measurements, go back, continue, then go back to the base station. So, by doing so, you have measured the variation in the gravity value at the base station at different times. When you plot this time versus delta G value, 6 a.m., 6:25, right, 7 a.m., we have decided to come approximately every 30 minutes, right. We cannot be precise. So, what is important is whatever is the time at which you are making the measurement, you please make a note, 9:31, then 804. Like that you are noting down the value. Using that we have prepared this drift curve. So, drift curve has got what? Both the issue with respect to the instrument and issue with respect to the tidal effects. So, here this author has nicely shown here, this is the issue with the instrument, instrumental drift, this is the issue with the earth tide only. Combinedly we have this effect. This is what we have arrived how during the measurement. We need not bother about what is the instrument drift, what is the earth tide effect. What is interesting is we need to obtain this in order to carry out the drift correction. Now, how are we going to do the drift correction? Similar to elevation correction or similar to latitude correction, what we have done is, this measurement was taken at 6 am. This measurement would have been taken at 6:11 am. This one maybe would have been at 6:23 am. They are all taken at different times, right? But using the same gravimeter. It is always the best to use the same gravimeter for the entire survey. Why? Because instrument itself has so much of drift, right? At different times it shows slightly different values, isn't it? So, we have to use the same instrument, right? Now, we have the drift curve prepared, that is what is shown here. Then we need to apply the drift correction. So, while applying drift correction, we may now decide what is going to be our reference time. It is left to us. Let us now imagine we are going to change the values we have measured at different times, making use of the drift curve as if they are taken at the same time. Which time? That discretion is within us. We will decide. Let us say I am going to change all the readings as if they were taken at 12 noon. How will I do that? Suppose here the readings that were taken, let us say at 6 am, how much it is different from 12 noon? 12 noon value is here. I will erase the rest all. Right, at 12 noon, the values we have obtained is this, right? Let us say it is 1.5 gravity unit, it is in gravity unit. I want to change, this is going to be my reference. Okay, that means this is the time at 12, this was the reading. Now, I have to convert all the other readings as if they were taken at 12 noon. Let us imagine this reading was taken at 6 hours. At 6 hours, what is the drift? Drift at 6 hours was almost, let us imagine it is at -1. Now, I want to convert that 6 am value as if they were taken at 12 noon. What I have to do? The value which I have taken at 6 am actually is much lesser than my 12 noon value. How much it is less? 1 on this side, 1.5 on the other side. So, here 1.5, here 1. So, 2.5 gravity unit, the value which we have measured at 6 am is lesser. So, what I do, the value which I measured at 6 am, I add 2.5 gravity unit. Is it clear? So, this is how we carry out the correction for the entire data. By carrying out correction, what we have achieved? we have achieved as if they were all measured at the same time, right? So, by doing so, we have completed diurnal correction or simply tidal correction, isn't it? So, what are all the corrections we have done now? First is latitude. What we have done? We have changed though the stations are located at different latitudes, after carrying out latitude correction, we have made in such a way, those stations are literally at different locations, we have now corrected as if they are all at the same latitude, isn't it? Next is free air correction. Those stations are located at different elevation, we converted them as if they are all at the same elevation. Boger correction, those stations are located at different elevations, thickness of the additional mass impact is different, we have nullified that. Then the next is terrain. In terrain, presence of valleys, mountains around our stations were removed. Lastly, we have seen tidal correction. In tidal correction, we have eliminated the effect of both the instrumental issue, which is known as instrument issue, which is the drift of the instrument, then the another issue is the earth's tide. Both were monitored by us by repeating the values at the base station. We have corrected the values we have recorded at all the other gravity stations in such a way the readings are taken at the same time. Now we have completed carrying out the important gravity corrections. After carrying out the gravity corrections, if the delta G value here is plus 3 milligauss, here it is minus 1 milligauss, right? If it is so, what does it indicate? So, here it is plus, here minus 1, right? If it is so, now at this value it is plus 5 milligauss. Now, what is the reason for changes in the gravity value? It is only because of the changes in the density of material present below this area, isn't it? Only for that purpose we have carried out the corrections. So, what we had seen after carrying out all the corrections, if there are still some errors, it is because of these reasons, right? Maybe if the vertical position is not accurate, that means elevation of gravity station, then we know already for every meter it is going to be 0.0386 milligauss per meter is the variation. Then this is due to the latitude. Then terrain correction will have an impact on that. Drift is going to be approximately this much. We have accounted for this, right? Then in Boger correction, we have to assign the density. Density of the subsurface difficult to estimate, isn't it? But we are approximately assigning based on our maybe 1 or 2 tests we can carry it out. We can carry out collecting the samples, but we do not know whether the density is the same everywhere or not. All this will lead to some error, but we have done our best to get rid of the errors due to latitude, then elevation, thickness of the additional slab, terrain, diurnal variation. Now, after carrying out all the corrections, now the data is ready for interpretation. Okay. So, in this lecture, we had focused on what are all the gravity data reduction which need to be given, which is also called as gravity correction. What are all the corrections we had learned today? First is the latitude correction, free air correction, Boger correction, terrain correction, lastly drift or tidal correction. After carrying out all these corrections, now we have the relative or absolute gravity values of all the stations. If their values are different, the difference in the values is only because of the difference in the density of rocks below this area. Now the data is ready for interpretation. Right? We will continue about how the data can be interpreted very briefly in the next lecture. Thank you very much.